All right, it's recording right now.
All right, perfect. I just saw it pop up. Good. Well, welcome everyone. Today's WebEx we're going to be covering how to do linear regression in R. That's going to help you with exercise 4 and your assignment that is due this week and next week. I think the exercise is due this weekend and the assignment's due next weekend. We'll do a quick run through of linear regression and what it looks like, and then we'll run through an example script using some student success metrics. The student success metrics are for a high school in Portugal, because it's amazing the sort of random data sets you can find when you Google things. So we'll run through how to do linear regression on that. We're not going to cover logistic regression directly, but the principle is very similar. The functions are the same. You would just need to use a binary target or a factor instead of a numeric target, but we'll get to that in just a second. So the first thing I wanted to do is just give you an idea, because it always helps me to have a picture of the model that I'm trying to build in my head before I start it. So you guys should all be able to see my screen. We'll get rid of this participants box right here. And you'll get a copy of this script too, so there's no need to try and copy anything down. But the first thing I wanted to show you is we're going to use some dummy data here. So I've just created two what's called numeric vectors. They're really just lists of numbers. And we're going to plot those two lists on a graph. I made these up. And what we do when we create a linear regression is we just draw a line of best fit through the middle of all those plots. So you should be able to see in this graph right here, right? We've got some dots. They're not perfect, but they're close to that line. And then we've just drawn a line of best fit through the middle of them. What this line does is it allows us to say that, well, if we don't have a dot exactly where we need it to make a prediction, we can say that, well, since they're all close to this line, I think if we had one in the middle here at, say, 12.5, I think the dot would be right about here, right in the middle. And that is essentially what we're going to do. Obviously, this has one variable and one response, one x and one y. We're going to do that with a few more variables, but that is the basic principle of what we're going to cover, is we're going to create that sort of a line. To do this in R, it's very simple. The function is actually built into R. There is no need to import any libraries or install any wacky software or jump through any of the hoops that some of the other models will have you jump through. In this case, we don't need to import everything. We just need to set our working directory so we can load up the data. And since the function is relatively simple to use, on the way to get to the function, we're going to step through a few things that are important considerations in terms of how you use a linear regression model. Some of the things that you're going to want to watch out for, and also a couple of little tips and tricks that I like to use. I work in R quite a bit. My background is in hotel analytics, so pricing and business analytics for hotels. So I work in R quite a bit, and there are a number of little efficiencies that you can use that help you make code more readable and a little bit easier to use. And I think they're very, 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 very helpful. So we'll pass a few of those along as we go through. So the first thing we're going to do, obviously, with any script is we're going to read in the data. This file is not a normal CSV. It's actually got a .csv extension you'll be able to see, but it's actually separated with semicolons. So if we pull that up here, you'll see that instead of it having commas between all the columns, we have semicolons, which means that if we just use the regular CSV function, it's going to read it in everything as one column because it can't find a proper delimiter. To fix that, we use this function called read.delim, so read.delimited, and then we use the argument sep to give it a different separator. This is really handy, and we use CSVs in air quotes, a lot with different delimiters when we're working with text data or when there's a lot of text data in columns. If you think about an address, you might have an address where each line is separated by a comma. If you put that into a CSV without special parameters around it, that comma is going to separate each part of that address into a separate field, and that might not be what you want. So we try and create CSVs, but with different delimiters. So we use a semicolon. You can also use what's called pipe, which is a straight line, and that helps prevent corrupted data. So to read it in, as I said, we'll just use this function, and then let's take a look at the data that we have. So as I said, this is a data about data from students who took a math course in a school in Portugal over the course of a year. And what we have is a bunch of demographic data, and then we have some grades for them at the end of the year, and we're going to try and predict what their grade was using this demographic data. So the first thing we'll look at is just take a look at the structure of the data. This tells us what each variable is, the types of response. So when it's a factor, how many levels does it have? Do we have integers? Do we have floats or doubles or decimal numbers? And how many variables we have? Obviously, we have quite a few. So we've got 395 observations, so records for 395 students, and 33 variables, a good chunk of which are these factors, so 1 or 2 levels. We do have a few with 4 or 5 levels, and we'll get to how we'll handle those in a second. Once we get working with linear regression, you're going to want to have your variables be numeric variables rather than factors. So we're going to code a few of those to be numeric rather than factors. Let's take a look now just again at a quick summary. With linear regression and logistic regression, we can sort of group the two together. There's a few things that we want to be particularly careful of when we look at our data that don't necessarily matter as much for other types of modeling. The first one is some of the ranges of data that we have. With linear and logistic and linear regression, the larger variables, so a variable that might be on a scale of like 1 to 100, ends up looking drastically different than a variable that's on a scale of 1 to 10. So we want to be aware of that when we go in, and we might want to take care of some of those by scaling the variables back so that they're either all on a standard scale or that there is some level of, so we don't have these big differences, right? And in most cases, in this particular data set, we're fine. We'll walk through what some of these variables mean as we go along here. You can see most of them, the max is 4. We have a couple where it's 5. I think there's a couple where it's 5. And then we have one where the max is 75. So this one, the number of absences that a student had over the course of the year, that's a variable that we're going to want to keep an eye on, because it might be that looks like a really important part of our model when we look at the coefficients, but it's actually not, because it has an enormous number associated with it. So the first time you pull up your data, you want to make sure you just do this quick sort through, make sure that nothing looks wacky. For the moment, we're not going to do any standardization. We'll come back to that in just a second. What we are going to do, though, is we're going to take some of these binary variables, so these factors that only have 2 levels, and we're going to turn them into numeric variables. When we run the logistic regression or linear regression and logistic regression in R, it does not handle factors. It doesn't handle factors very well at all. So we need to make sure that we put in numeric variables instead of factors. And we need to encode them properly. There are a number of different packages you could get that you can work with to try and encode these variables. I've had mixed success with them. Some of them work very well for some data sets and very poorly for others. Some of them work, as far as I can tell, very poorly all around, and some of them are all right. Since we don't have very many variables in here, I'm going to code them all in by hand. I did the annoying typing of everything so that you don't have to. So you can just copy and paste this sort of thing into your script if you want to run the same thing. And all we've done is we've assigned a 1 or a 0 to each level of the factor based on whether it's, so in this case, whether you're female or male, you get a 1 or a 0. In this case, when we're looking at address, it's not really address, it's actually an urban versus a rural address. So for urban addresses, we've given them 1. For rural addresses, we've given them 0. Family size, again, is 2 levels. And then yes and no obviously get a 1 and a 0. We've coded in all of the 1s and 0, the binary attributes. The factors with more than 1 level, we want to be a little bit careful with. And again, this is something we that's going to come up again. So we'll just let's run all of those, get them into our data, and then take another look to make sure that they all came through correctly. And you can see here we've got all of these other ones with .num on the end. So we've correctly converted them from factors. Well, we've created extra variables that are numeric instead of factors. So that brings me back to a couple of these other ones, right? So let's pick M job and F job. You guys read this, they're kind of small. So M job and F job is the mother's job and the father's job for each of our students. And we have 5 different options for what their job could be, what their industry they could work in is. When we assign a number to those jobs, particularly with regard to linear and logistic regression, we are assigning a weight to that, sort of, not really, but sort of. And what that means is that when we say that at home is a 1, health is a 2, other is a 3, service is a 4, and teacher is a 5, we're saying to our model that a teacher is worth 5 times an at-home person, and a health is worth 2 times an at-home person. So since there's no natural order to these type of variables, we're going to leave them out of our model. Because we don't want to say that, we don't want to artificially influence our model to make it think that when you're a teacher, that somehow has 5 times the value of being at home, or is 1 better than working in services, or is 2 better than other, whatever working in other may be. And that's important. The way to identify those variables is to think through, is this a variable where 1 level is worth more than another? So if you had something else, say this was a like salary ranges instead of jobs, and you had like, I don't know, 0 to 10,000, 10,000 to 20,000, 20,000 to 30,000, 30,000 to 40,000. Those we could order, those we could assign numbers to, because they have a natural order, right? 0 to 10 is below 10 to 20. Whereas for other things, it's a little bit more difficult for us to assign specific numbers to them. And in the case of logistic and linear regression, we want to steer away from those if we have the option to do so. Since we have such an enormous number of variables compared to the number of observations in this data set, it is safe for us to do so. All right, so how are we doing? Any questions? Are you guys confused? You still with me? Did I put you to sleep yet? I'll take that as a no because I heard somebody laughing. That's a good start. So now we've recoded some of our variables. We have enough variables now that we can begin working on creating the model. Here's one of the tricks that I like to use. Before we create the model, I like to know which variables I'm going to put in my model. And I like to store them in a single place so that if I suddenly decide that the numerical representation of whether somebody's in a romantic relationship, romantic.num, if I suddenly decide that's not relevant, I can delete it in one place, and then I can rerun all of my models without having to go through and delete it in each thing. To do this, I do what's called creating a list. So this list here that we're going to create is keep.vars. all you do is you just do C, the letter C, lowercase c, and then you put in all of the variable names separated by commas. When we run this, we get a list of keep.bears. So if we pull up this list, you'll see that now I have a list of all the variables I want to keep in my data frame. Oh, sorry, I want to use from my data frame in my model. What this does then is it gives me a way to filter out different parts of the different columns, right? So here we have two different ways of doing that. If you guys learned some SQL in the last course, some of you I TA'd for, in SQL there is a function that called in, so you can say, is this in this list of variables? And what we're doing here is a very similar thing. So if I had to walk you through this one, we're looking at the data frame. That's obviously where all our data is. We're saying if the column names of my data frame are in the list of variables that I just created, then we're going to keep them. And if they're not, we're going to ignore them. So if I run a summary on this, because this is obviously, since we're doing linear regression, this is all of my numeric columns. If I do this and I look at the summary of that, you see I have all of my numeric columns. And I haven't got any of the ones that aren't in this list, which are the factor columns, particularly those with several levels that we talked about. If I have a lot of variables, sometimes instead of doing a list of variables I want to keep, I might do a list of variables I don't want to keep. To do that, the function is exactly the same, but you add an exclamation point in front of this names data in keep theirs. That will exclude everything where the column names are in this list of variables. So if we run the summary on that, you'll see that here we have all of the old factors, right? So all of the ones before we converted them to numbers, along with those other ones that we didn't like, and a couple of extra target columns here that we're not going to work with called G1 and G2. So that is a little trick, and you'll see that as we go through, we use it again here to create the training and test data sets, and then we use a slightly different one a little bit further down, which we'll get to in a second. So having done that, we're now going to create our training and test sets. Training and test sets are a pretty important concept, as I'm sure you guys have discovered in your reading. When we build a model, any type of model, we want to make sure that we're testing it on a data set that we didn't use to create it. The reason for this is, and I'll tell you a story. Some of you guys know that I went through this program. The very, very first course, the very, very first one, I discovered that I could build up an awesome model that was like 98% accurate because I kept training it and training it and training it and then feeding it the same data to test it on. So the more I trained it, the better it got, and I thought this was fantastic. But of course, it didn't work actually in practice. And the reason for that is because when you train a model on the same data that you test it with, it's going to be pretty good. That's like using flashcards. Whereas what we want to do is find some different flashcards that we haven't shown it yet and make sure that it generalizes well so that it will work with other things. So to do that, we're going to create a training and test set. The first thing to do before you do any sort of sampling is set the seed. I like to use the seed number 42. 123 is a popular one too. It doesn't matter anything what you use. I use 42 because I'm a big fan of the Hitchhiker's Guide to the Galaxy. And if you don't know what that means, then you should read the book because it's fantastic. So having set the seed, we can now create a list of ones and twos that we're going to use to separate out our training set. So the sample function, I'll show you. So the sample function gives you random samples of different numbers that in a number of different ways. What we're going to use it for is we're going to take two numbers. We're going to create a list of those two numbers that is as long as our data. And we're going to select them with a probability of 0.7 for the first number, which is 1, and the second number, 0.3 for the second number, which is 2. What that's going to do is it's going to give us a list of 1s and 2s, and then we could say when it's a 1, I want it to be part of my training set, and when it's a 2, I want it to be part of my test set. There are a variety of different ways of achieving the same task. This is very efficient. You can also do the same thing using a slightly different sample function, so sometimes you'll see this looks slightly different, but it's fundamentally doing the same thing. It's creating a list that we can use to separate out our training and test set. And if we look at this list called int, you'll see we got 2, 2, 1, 2, 1, 1, 2, 1, 1. So all of the numbers, all of the rows that associate with a number 2 in this list will be part of the test set. All of them that associate with a number 1 will be part of the training set. And then right here, we're going to create the training and test set, as I said, using when int equals 1. So when this list is equal to 1, it will go in the training set. And then we're going to use the same function that we did up here. So we're going to say, and when the column names of our data set are in this list of variables that we want to keep, we're going to keep them. We're going to keep those as part of the training and test set. So let's do that and create those. All right. And having gone through all of that ludicrous rigmarole, we can now create our model, which takes exactly 2 lines of code. Actually, it takes exactly 1 line of code if you put the model in the thing, but that's not the point. Again, we're creating a model using a formula here. The formulas in R are a really helpful way of understanding how your model is going to be created. For the most part, they take the form of whatever your response variable is. In this case, we're going to be using G3, which is the grade the student received in the whole course. And then it's like G3 given the little squirrely funny thing. I think it has a name, but I forget what it is. It's shift and the key next to the 1 key on most keyboards. That's how I remember it. And then dot means everything in the data set. You could also, if you wanted to create a more specific formula, so we could do my formula too. We could say I want it to be G3 given, and then internet.num, which is 1, and then we would say plus, say, famrel, which is the quality of family relationships. And we could do that. And that way it would just use those 2 variables. This dot uses all of the variables that are available to it, which we can do because we filtered out the ones that we don't want by creating our list earlier on. All right, so let's get rid of this second formula here. One interesting thing to note as we're training this model here, if you wanted to build this model, you can actually put the formula inside the model. So where it says my.formula here, we could have just typed in this, but you do it without the quotation marks around it. So if we wanted to put that inside the thing, it would just be G3 given everything, comma, data equals train. And then that will do the same thing. Whoops. Help if I could spell train. There we go. So that does the same thing, but we just want to, you don't need to put the quotation marks around it when it's actually part of the thing. So this, so now we have a model. We have a model. We trained a model. Let's take a look at it. All right. So this is telling us all about the linear model that we just trained. There's a whole bunch of information on here. Residuals, which is basically the error, how far the predicted values are from the actual values. Then we have our R squared down at the bottom here, which is about, so 0.22 is not fantastic, frankly. means we explain about 22% of the variance in grades using the variables that we gave it, which is, as I said, not fantastic for classroom terms, but in the real world, I wouldn't be unhappy with that. Certainly gives us a little bit of things. And then for each variable, each independent variable that we put into the model, it tells us what the impact was on the dependent variable. The two most important columns to look at here is this first column, which is the coefficient. So that tells you whether it has a positive or negative influence. And then this value on the right-hand side, which tells you the statistical significance of that relationship. So you can see that in a number of cases here, we don't have a particularly good relationship between that variable and whether somebody gets good grades. But in several cases, we do. So first off, the number of times they've failed a class has a very strong impact on it, very strong relationship between those two, which is not that surprising. The amount of time they spend going out, the higher that is, the lower their grades. Whether they are male or female has a statistically significant impact on it, as well as whether their family receives like supplementary income, whether their family receives welfare or I'm not sure what the Portuguese equivalent is, but that's what that means. And also up here, the amount of time they spend studying. So these R gives you these helpful little ... things. The significance codes are listed down here, but basically the more stars there are, the better. 1 star is p-value of 0.05, which is sort of the standard. But in a lot of cases, I mean, 0.1 is reasonable too for some of these models. So this tells you which variables are helpful. Now, to take that a little bit further, we can take a look at how well our model did in terms of predicting things by creating some new predictions on our test data and then plotting those on a graph. So we're now going to create a vector of predictions. To do that, we use the predict function. The predict function just takes the model that we just created. So model is the model that we built up here with our linear regression formula, and then it takes an argument called new data, which is just the new data that we want to make predictions on. One of the things you want to do is make sure that whatever new data you pass in has the same variables as the the training data that you used. If that's missing a column or something wacky is going on, then in most cases the model will throw an error. Sometimes it won't. It will just give you weird results, and that always makes it particularly entertaining. So that gives us, as I said, this vector of predictions. So you can see it's just a list of numbers up here. So let's go ahead and plot those two on a graph, and we'll look at what our predicted grade was versus what the grade actually was. And you can see there's definitely a little bit of a positive correlation between those two there. In fact, we can use the linear model formula again to draw a line of best fit through that, and you can see that our model did begin to predict higher grades when students received higher grades and slightly lower grades when they received slightly lower grades. We did miss all of these zeros on the left-hand side here. So potentially, if we were really trying to predict, we might have wanted to throw those out of the data in case they skewed it. Excuse me, but in this case, I think we're good to leave them in. The other thing we can do is take a look at some of the plots that come along with the model. So to do this, we'll just call the plot function around the model. And it's going to give us some different options. This is little bit annoying. You're up here and you click on it, then you have to go down here into the console and just click through some of these. So we'll hit enter, and this will show us the first one, which is just a graph of residuals versus the fitted values. So what the errors were and where they lay, basically how much we missed by for certain levels of G3. A couple of other things showing us, again, residuals. You can see that in the middle of the range, we were much better than we were at the end of the range, usually because there's more data in the middle of the range. And then, again, just a different version of the same thing here. So we're looking at the fitted values. So when we predicted a 14, here's some of the errors that sat around it. And then, again, more about where the errors lay. We would want to look through these plots in a lot more detail, particularly if we're trying to do something predictive with these. From a data mining perspective, what we really want to understand is the influence each of those variables had on, in our case, what a student's grade was during the course. And to do that, we use a function called coefficients. I'm going to call that on the model. And this is going to give us a list of all of the coefficients for all of the pieces of our model. Now, this is kind of fugly, frankly, and a little bit difficult to read. You can also use this to look at the coefficients, but again, it's not particularly good to read. But I think this shows us somewhat what we'd expect, right? Which is always good, because when a model is too counterintuitive, then we get very suspicious of it. For example, this says that age has a negative impact on the grade, so the older you are, the less likely you are to get a good grade. Mother's education and father's education, so the higher the level of education the parents have achieved, the better the grades of the student. Longer travel times, interestingly, result in higher grades, although that wasn't particularly significant. In fact, if I remember rightly, I think that was pretty poor. The time spent studying, the more time you spend studying, that has a positive impact on the grades. Failures, obviously, as we saw earlier on, that has a fairly negative impact on the grades, and so on and so on and so on. And we can run through each of these in turn. I'm not going to walk you through every single one. I think you guys have got the impression for how to use them. The one thing, or a couple of things to remember when you're looking at coefficients with a linear model. Well, really, two important things. If these variables are not independent, so if one of these variables could have an impact on one of the other variables, then the coefficient may not represent the full impact of that particular variable. I'll give you an example, because that is a very abstract thought, right? If somebody's health has a negative impact, or sorry, a positive impact on the number of absences, then it's not clear when we ask the computer to look at the data whether, well, is it the fact that their health is poor that's causing bad grades, or is it the fact that they had a lot of absences that's causing bad grades? And in that case, what the coefficient represents is not necessarily the full effect of that variable, or not necessarily the correct effect of that variable. The second part of this, which is closely related to that first part, is each of these coefficients represents the impact that this variable has on whatever our response is. So in this case, it's the impact that this variable has on our grades that's not represented by another variable. So what does that mean? It means that mother's education has a coefficient of 0.4, which is quite strong. 0.4 is the impact that is explained by no other variables in here. If some portion of the impact of the mother's education is also explained by another variable, and that's not necessarily taken into account in that coefficient. The practical upside of this is that if you have variables that are closely correlated or variables that are closely related, you can end up with fairly wacky results where one variable appears to have a positive impact on the model, but really what's happening is you have one variable that has a massive negative impact, another variable that has a fairly significant negative impact, but actually, because most of its negative impact is being explained away by another variable, it ends up with a positive coefficient. That sort of thing happens, as I said, when you have these closely correlated variables. To identify them, certainly with small data sets, you can look through and be like, well, I think these two would probably have an influence on one another. You can look at the correlation. You can look at a correlation plot between different variables. You can also just run different linear regression models without certain variables in it to see what the impact has. So it's funny we should talk about that, because one of the things that I thought when I first ran this model, let's pull up the model again real quick, is that frankly, we have a lot of stuff in here that's not particularly statistically significant. We've got a handful of good variables, but we've got a lot of stuff here that doesn't look like it's helping a whole lot. So what happens if we cut the model back and we only run it?
What will help you? Otherwise,
What's that? Oh, I think we're good. Are we good? Good deal. So what happens if we take these good variables and we just run the model again with the same variables? So what we're going to do is we're going to put the good variables into a list, as we talked about with our response variable here on the end. We're going to create a second training and test set. Again, we're actually using the same split as we did the first time. So you see int equals 1, and then this time we're saying whether the names are in this list of good variables that I just created. Excuse me. And then we're going to create a second model, and then we're going to look at the second model. All right, far fewer variables, much better effects. So these do have obviously slightly different coefficients. We're actually explaining away a little bit less of the variance in the response, right, in the grade. Last time we were about 22%, now we're about 15%. So that's not ideal. But we do have some more statistically significant results, which is good. In particular, gender appears to play a role. The number of, again, failed courses appears to play a role. So that has shifted around a little bit what we're looking at, and given us maybe a better view of the impact each of these variables is actually having on the grades of the students in this class. Now, doing that yourself is, well, to be frank, it's a bit of a pain in the backside, because you have to read through this list and then you have to go, well, is this one good enough? I don't know. I kind of like this one. There is a function built into R that does that all by itself, which is very helpful. We can use this function called step. What step does is it takes all of the variables and then it basically optimizes the model. So it's going to step through by removing the least helpful variable, rerunning the model, and then it's going to remove the next least helpful variable, and so on and so on and so on, until it comes to a happy place, so to speak, where it has a good balance between models that are explaining away a good portion of the variance and a model that hasn't gotten so few variables in it as we did, right? Because we cut it back pretty significantly, and we ended up dropping our R squared to only 15.65 or 0.165. So let's go ahead and run that. Create a third model, and you can see a bunch of stuff flashed up on the screen because we scroll back up to the top. It's a long way up to the top. You see it starts off with all the variables. Then it says, oh, there's a couple that suck. I'm going to get rid of those. So it gets rid of them. It gets rid of a few more, and so on and so on and so on and so on and so on. till we go all the way down to the bottom, and we've cut it back to a handful of variables, which we can see when we look at the responses here. And you see this has done a little bit better job of selecting variables than I did. We have a better R squared, 0.1934. We also have some more statistically significant variables. So now the mother's education does appear to have an impact. The amount of study time has a positive impact. Failures has a negative impact. Strong family relations have a good impact. If you go out too much, that has a negative impact. And then so on and so on and so on. So what that's done essentially is optimize the model and got rid of all the variables that don't really explain very much of the variance. Doing that is going to help us put a bit more faith in what these coefficients are telling us about the impact of certain variables, or at least the correlation of certain variables with our response variable. So that is the end of that particular script. Any confusion or questions or things that you guys would like to bring up? Feel free to unmute yourselves if you want to talk, or you can type something in the chat box. Mm-hmm.
Hey, John, I have a quick question. So when you run your summary model 3, and you mentioned some of them has the positive relationship and some of them has the negative relationship. So how do you figure out just looking at those numbers?
So we're looking at, to figure out whether something has a positive or negative relationship, we're looking at the coefficients. The coefficients I showed you, you can bring up with this coefficients function, and it brings you up this list. They're also listed in this summary in the estimate column, because, you know, calling it coefficients would be too easy. So all of these are the coefficients. So you can see that when something has a positive impact, it will have a coefficient above 0. When it has a negative impact, it will have a coefficient below 0. Because if you remember the basic formula for linear regression, and this is, we're getting into mx plus b, right? So b is our intercept, which is this line up here. And then m, which is the coefficient. If m is positive, then we'll have a positive slope. So it will have a positive impact. If m is negative, then we'll have a negative impact. So what we really have here is we have like y equals mx plus b, mx plus x plus mx plus, etc., etc., etc. So each of these is that one. So plus positive impact minus negative impact. And then the size of the coefficient tells you a little bit about the size of the impact too, right? So failures obviously has a big negative coefficient, 1 minus 1.6. So that's a pretty hefty impact. Whereas, well, we're about half a point with each of the other ones. You know, some of these other ones, maybe family relationships has a positive impact, but not nearly as significant a positive impact as some other factors. Does that answer your question?
Yes, thank you.
Yep, good deal.
Yeah, I had one additional question. When you remove the factor variables, when you have more than one levels, that part I quite didn't get it. If you can explain me one more time.
Yeah, sure. So if you think about what we're telling the model when we put in a variable, so let me come at this a different way, maybe. So there's 3 types of factor variable that we could have, right? You can have a nominal variable, which is there's no order to it. There's no natural order. That's like your job. What's your job? All right. There's no way to say that one job is better than another job, objectively speaking. Say one job is better than another job. One table is better than a different table. One color is better than another color. There's no way to order those in a logical way, right? Not in an objective logical way. Then we have what's called ordinal variables. Ordinal variables do have a logical order, but they're still categorical. So that might be something like, let's say there's no order. So something like, go with color. That could be our example. Ordinal might be something that does have an order. So say we have a classification of size. So if we said small, medium, and large, right, those have an order. You can say that a small one is small, and a medium one is in the middle, and then a large is next. When it comes to encoding those into numbers, because we can't say with a nominal variable that brown is better than blue, or yellow is worse than green, we can't really put a number to that. Because if we do put a number to that, when we put that into the model is going to treat it as if that scale is a scale. It's not just going to treat it as if it doesn't have a proper order. Whereas in this case, right, when we get to the ordinal variables, you can say that we could encode these as 1 for small, 2 for medium. Whoops, apparently my numpad isn't on. So 1 for small, 2 for medium, and 3 for large, right? Because you can objectively say that large is bigger than small. There's an order to it. Does that make sense, or is it still? It's
making sense.
Yeah, it's a tricky little concept, and when to use one or the other is not always immediately clear. So it's something to watch out for. The way you would handle this, in case going further into this helps out a little bit, is that typically for an ordinal, right, we put them on a scale. So you would say 1 is small, 2 is medium, 3 is large. If we had colors, say we have blue, orange, and red, what we do, whoops, that's not very helpful. What we do is we take those 3 colors, and instead of having one column that had blue, orange, and red in it, we'd have a blue column, and that had a 1 or a 0 in it. And then we'd have an orange column, and that would have a 1 or a 0 in it. And then we'd have a red column, and that would have a 1 or a 0 in it, right? Because that does have an order, because you can say that blue is, if it's blue, it's 1, if it's not, it's 0, if it's orange, it's 1, if it's not, it's 0, if it's red, it's 1, if it's not, it's 0. So we'd spread those into different columns instead of having a single column for all of them. And again, there's functions for that, so you don't have to write out each individual column, because that is incredibly tedious when you have a large number of variables. But it does help. In a lot of cases, it's going to help you get better results than just arbitrarily assigning numbers to something like colors where there's no natural order to them. So any other questions? Excuse me. Whoop. I see Susan has a question. Let me pull it up in the chat here.
So John, so what would be the difference? I know you mentioned it earlier about the logistic regressions. So what would be like difference between the linear and logistic regressions?
I will grab that in a second, and then we'll talk through with Susan's question here, because Susan's question is a good one. Why are we saying that the first model, with all the variables and the highest R squared, is not better than the third model, which had a lower R squared and fewer variables? The reason for that let's put it bluntly, the more variables you have, the more chance there is that one of them is going to be wacky and it's going to go wrong and it's going to cause your model to get poor results. So what you want is the best model using the smallest number of variables that you have. Now, that's abstract. Really, it's going to depend case by case what the difference is in R squared between the two models. So by eliminating all those variables, we went from 0.22 to 0.19. It's not a huge drop. If we'd gone with the way I did it, right, where I selected them and we went down to 1.5, it's probably a bit too big. But ultimately, it really depends on the application, which one the best, in air quotes, model is. So it's really, again, you're trying to balance the degrees of freedom, like how much space you give the model to vary with the overall objective accuracy for it. So again, I'm not sure if you guys can see Susan's question up here. There isn't. So the metric for best is somewhat subjective and somewhat depends on the application. Am I concerned enough that one of these additional variables that I'm including could cause errors in the prediction? Am I worried enough about that I'm okay with losing a little bit of accuracy by getting rid of some of the variables? In some of the cases, I probably am. If you look up, so this is model 3, right? If you look at the p-values, they're pretty good. If we go back up to model 1, and look at that again, we have some pretty high p-values in there. And what that means is really we don't have a lot of confidence that some of these variables, right, like health, with a p-value of 0.94, we're not sure that's statistically significant. So we don't really know whether that coefficient's the actual coefficient or it's much higher or much lower. So if we get an extreme value for health, that could have a significant impact on the prediction that we make, even though we didn't necessarily expect that or anticipate that. So it is, there's no metric for picking the best except accuracy, but you do want to balance that. So there is a little bit of a trade-off in there. Good deal. I wasn't sure I could explain that any more wackily. Wally asks, as we optimized for Model 3, the system was removing the variables that had, like what criteria was it using for removing the variables? It's going to remove the ones that are least stable so that they have a high p-value. That's not the direct criteria it uses. It uses something called information. Information is a sort of mathematical concept which is easiest to think of in terms of ones and zeros. So if we have a bucket full of ones and zeros and a bunch of ways of separating them, the variable with the most information is the one that gives us the purest separation of all of those ones and zeros. So that's what it's doing, sort of. It's basically saying how much extra information does this variable give me? Information in this case in terms of accuracy and stability with a p-value. And if it doesn't feel that it gives it enough information, it's going to kick it to the curb and try a different one. Does that answer your question? And then, Mohammed, do you mind repeating your question again? It slipped my mind.
Yeah, I wanted to ask you what's the difference between the linear regression and the logistic regression?
Oh, that's right. Yeah. So linear regression, if we go back to my little fakey plot at the beginning here. Let's close that. Close that. Excuse me. So logistic regression is a scale that goes on forever, right? If I predicted a value of 1,000,000 on this x-axis, it would have a corresponding value on the y-axis. And we use it for numerical prediction. So you use it for anything that's on a large scale. Logistic regression is used for classification, and it gives you a 1 or a 0 corresponding to whether it's in a certain class or out of a certain class. And it does that by constraining this line so that this line will only ever move between 1 and 0. Trying to think of whether there's a way I can pull it up. Basically, if you imagine this being like an S-curve. Oh, here's a good idea. So instead of being like this, it will go, I'm going to attempt to draw this with a mouse, sort of out like this, and then down like this, and then down like this. And no matter how extreme the value, it would never go below 0 or above 1. I've lost my mouse. Where is it? There it is. Or above 1. Which means that something else that never goes below 0 or above 1 is probability. So the value that you get from a logistic regression is the probability that a particular item is in or out of that class. It's fundamentally the same as, but mathematically it's the same as a linear regression model, so the straight line, but with a mathematical transformation on it to constrain it between 1 and 0. Does that make sense?
Yes, it does. Thank you.
Yeah. And basically everything that you do to create it is almost identical to this. You just give the LM function, wherever it is. Right here, you just give that a factor as a target, or a 1 and a 0 as a target. I think maybe it tells us actually. Maybe not. There's another trick. You guys know about the question mark, right? If you put a question mark in front of a function and then run it, it gives you the help for it. It's the best R feature ever. The ability to look stuff up on the fly. Good deal. Any other questions? Cool. Well, I think that wraps us up then. I will obviously share this script and the data and the cheat sheet here with what all of the attributes mean with you guys along with the recording once we get that posted up. If any other questions come up, then please feel free to shoot me an email or post something in the questions for the TA discussion forum. And cool. Thanks for listening. I will talk to you guys soon.
Thank you, John. So, John, I'm going to end the recording. Thank you.
Sounds good.